Good evening, everyone. I'm Akila Reddy Karumudi. Today, I'm going to present my final project for the recurrent neural network. This project consists of 7 parts. The first part is about selecting a dataset, a time series dataset. So, I browsed a few datasets in the internet and I found Federal Reserve economic data as the useful dataset for this part. This dataset represents the number of employees in the manufacturing sector in the United States, measured in thousands of persons and seasonally adjusted. It is part of the larger economic dataset provided by the Federal Reserve economic data, and the dataset information has uh, the data type is the numeric. The dataset consists of time series data, which is monthly wise, and there were two columns, date and man m. Date is for the dates of the observation, and the other one is number of employees in the manufacturing sector. So this time series span starts from January 1939 to November 2024, the latest observation. Total duration is for 86 years. The frequency is monthly observations. The number of data points in this data set are 1032 observations, as there are 12 months per year, as there is 86 years observation. The data structure columns is data and manam, the month and the year of the observation. I have downloaded this data set in CSV format. So this dataset is used for analyzing employment trends in the manufacturing sector, for studying the impact of economic policies on the manufacturing industry, developing predictive models for employment forecasting. So the critical insights that can be observed from this dataset is the regularity. The dataset provides consistently monthly updates, making it ideal for time series analysis. The second part is about simple RNN with sine wave data. This is the diagram of RNN. I used 64 neurons for my simple RNN layer, and it has an output layer and a dense layer. So this is the architecture. Input layer has a sequence of 50 time steps. This layer is utilized to feed the RNN layer with sequential data. So the RNN layer has 64 neurons. It feeds the sequence into this layer along with the internal state and processes it. So after processing the sequence, this generates a vector of 64 dimensions at the last time step. The next layer is the dense layer, which is also called as output layer. The fully connected layer containing one neuron. It will take the final output from the RNN layer and generate one predict value. The simple recurrent neural network two-layer architecture is for capturing sequential patterns of a time series to predict its next value. These are the project results report of my simple RNN layer. The architecture of the model was set up using a simple RNN layer followed by a dense layer as said in the architecture. So the network has 4289 trainable parameters in total. The compilation model used for this is Adam optimizer and the mean square error loss. So this is the performance of training after the model has been trained. It has been trained over 5 epochs. With each epoch, the MSE loss decreased, reaching a final loss of approximately 3.8 into 10 power 5. This indicates successful learning as the loss continuously minimized during training, demonstrating the model's capability to effectively learn the sine waves and underlying pattern. So training loss visualization, epochs plot, the plot shows a step decline in the first few epochs. I'll show you the visualization in the next slide. So starting from 0.032, it has been reduced to 0.00005. So this is the plot. There is a gradual decrease in it. So the prediction values are also calculated by writing a Python code in the Jupyter notebook. So the code used is for two predictions is this, and the final prediction result is also shown here. The data point with the sign value of approximately minus 0.803, the predicted value was 0.8076, reflecting a very small deviation. Sorry. Okay, the third part is about LSTM neural network. So, vanishing gradient problem, explanation and its cause. During backpropagation, the gradients of weights in earlier layers can become extremely small, almost vanishing. So this happens because of repeated multiplication of small gradients across many layers of time steps, leading to exponential shrinkage. So the cause is because of the activation functions like sigmoid and tan have derivatives in the range 0 to 1. In RNNs, this happens because of the backpropagation through time involves gradients following across multiple time steps. So in contrast to vanishing gradients, exploding gradients occur when the gradients grow exponentially large during backpropagation. The cause is because of the large weights or inappropriate initialization can lead to excessively large gradients, especially with long sequences. Uh, so, uh, Limitations of simple RNN neural network. So these are the drawbacks in simple RNN: the short-term memory, vanishing gradient problem, limited capacity, difficulty in handling complex sequences, stability issues. So coming to the short-term memory, simple RNNs can only retain information for short sequences. They fail to capture dependencies over long sequences due to the vanishing gradient problem. Vanishing gradient problem is, as discussed, simple RNNs suffer from the vanishing gradient problem, making it challenging to learn long-term dependencies. Limited capacity. Simple RNNs lack mechanisms to selectively retain or forget information, unlike LSTMs and GRUs, which have specialized gates for these tasks. The stability issues in simple RNNs can be prone to exploding gradients if not properly regularized. So, difficulty in handling complex sequences in simple RNNs struggle with tasks that requires learning hierarchical or complex temporal patterns. How these LSTM addresses gradient problems and simple RNN limitations. So gradient problems are cell state, forget gate, constant error carousel. So LSTM introduces a cell state that allows gradients to flow through time with minimal changes, preserving the gradient's magnitude. Controls which The forget gate controls which information to discard from the cell state, helping avoid unnecessary gradient buildup. And constant error carousel enables the network to propagate errors unchanged, effectively mitigating the vanishing gradient problem. Addressing these limitations, the selective memory, LSTM uses gates to regulate the flow of information, enabling the model to retain or discard information as needed. Long-term dependencies. The architecture explicitly supports learning long-term dependencies, solving the short-term memory issue. So this is about the third part. Coming to the fourth part, LSTM with time series data. This is the design of the neural network, which has input layer, hidden layer, one more hidden layer, and the output layer. So the LSTM neural network was designed to handle time series data efficiently, leveraging its capability to learn long-term dependencies. The architecture of the neural network includes the input layer, which accepts the time series data as input, feeding it into the subsequent LSTM layers. Hidden layers are three LSTM layers are included, each capable of capturing sequential dependencies and temporal patterns. Dropout layers are added after each LSTM layer to prevent overfitting. by randomly deactivating a fraction of neurons during training. Output layer. A dense layer is used to make the final predictions, producing a single value for each time step. The model was built with a total of 50,851 trainable parameters, which reflects its ability to learn and adapt to the complexity of the data. The combination of LSTM and dropout layers ensures a balance between capturing the data's underlying patterns and avoiding the overfitting. So the summary of core parameters are percentage of data for testing is 10% has been used of the dataset was reserving for testing, ensuring a robust evaluation of the model's performance. So number of LSTM layers used here are 3. The network comprises 3 LSTM layers to effectively capture temporal dependencies in the time series data. Number of neurons per LSTM layer used are 50. So each LSTM layer contains 50 neurons, providing sufficient capacity to model the complexity of the data. So dropout layers. 2 dropout layers were included after each LSTM layers to prevent overfitting. Percentage of dropout layers is set to 20%. A 20% dropout rate was applied, meaning 20% of the neurons were randomly deactivated during training. Length of the input sequence. The model was trained with a time series input sequence length of 60, representing the previous 60 time steps for prediction. Batch size for training. A batch size of 30 was used during training for computational efficiency. Batch size for testing and forecasting. The batch size was set to 1 for testing and forecasting, ensuring predictions were made one step at a time. Number of epochs for training. The model was trained for 100 epochs to allow sufficient learning while avoiding the outfitting. So these parameters were carefully selected to balance computational efficiency, model complexity and performance, ensuring the LSTM network could effectively learn and predict time series trends. So these are the results after after writing the code and running each cell for LSTM project in Python. So this is the architectural model as explained. 50,851 trainable parameters were used, and the compilation method, the model was compiled using the Adam optimizer and mean squared error. Performance of the training. The model was trained for 100 epochs using the training data generator. The training loss showed a consistent decline, demonstrating the model's ability to learn effectively over time. The initial loss started at 0.0521 in the first epoch and reduced to 0.0021 by the 10th epoch, showing rapid improvement with the early epochs. This indicates that the model adapts quickly, achieving a low error rate within a relatively short training period. These are the epoch values generated. So epoch wise training loss. Initial epochs, the loss decreased rapidly, starting from 0.0521 in epoch 1 and dropping significantly to 0.0021 by epoch 10. So middle epochs, the loss showed slower but steadily improvement, stabilizing between 0.0020 and 0.0012 during this phase. The final epoch was between the range of 0.0008 to 0.0011. This consistent low loss indicates that the model achieved stable performance and effectively learned the data's patterns. Training loss visualization. The training loss plot demonstrates that the LSTM model effectively optimized for the task. The loss decreased sharply during the initial epochs and stabilized at a low value as training progressed. The final loss converged to a steady rate of indicating the model's ability to capture patterns in the training data without overfitting. The gradual stabilization of loss after around 20 epochs suggests effectiveness learning and regularization. Um, so these are the visualizations, and the LSTM model successfully predicted future data points based on the test input sequence. The predictions can now be visualized against the actual values to evaluate the model's performance further. The smooth progression in the normalized predictions highlights the model's ability to understand and forecast sequential patterns in the time series data. So this is the prediction values, data points for testing. Prediction visualization analysis. The visualization confirms that the LSTM model performed well in predicting future data points, with the forecasted trend closely following the observed historical behavior. This highlights the model's stability for time series forecasting, providing a reliable basis for analyzing and interpreting future trends. So this is the visualization for the prediction values. The training results for LSTM model. The LSTM model was successfully trained on the time series data for 100 epochs using the FIT method, with the training loss demonstrating an overall declining trend despite some fluctuations. Starting from 3.9 to 10.4, the loss stabilized around 3.7 by the final epoch, indicating effectively learning of temporal patterns and strong predictive capability. The loss fluctuated occasionally during the middle epochs. In the final epochs, the loss converged to values between 2.8 to 3.7, showcasing the stability and suggesting the model avoiding overfitting. This low final loss highlights the model's readiness for accurate forecasting through though further evaluation on the test data and fine tuning could enhance the performance and minimize the fluctuations. So forecast data frame analysis. The provided data frame forecast DF contains 500 rows within a single column, so named forecast, representing the model's predicted values for future time step. So these are the forecast values. This structural data frame facilitates each visualization and analysis for forecasted trends, highlighting the model's ability to capture long-term patterns in the time series data. So this is the forecast plot analysis visualization graphs. The visualization display two primary plots. The first one is the historical close prices and the forecasted values. The first plot captures the historical data, revealing an upward trend followed by periodic fluctuations representing the stock price. The second plot, which focuses on the forecasted values for 500 future time steps, illustrating a smooth downloaded trajectory predicted by the LSTM model, stabilizing at approximately 74.71. This indicates the model's projection of a declining trend in the price based on the temporal patterns. The separation between historical and the forecasted data provides clarity for analyzing the model's prediction and assessing their alignment with the past behavior, enabling informed forecasting insights. This is the final visualization graph. The plot provides a combined view of the actual closing prices, which is blue line, and the forecasting values, orange line, for the dataset. The actual closing prices show a clear upward trend with fluctuations consisting with historical market behavior. In contrast, the forecasted values exhibit a steady downward trajectory, stabilizing at lower values. This significant disparity suggests that the model's prediction deviate from the observed market trends during the specified period. So in the part 6 we are asked to redesign the neural network. So I tried changing multiple parameters so that a better performance can be viewed. So this is the design of the neural network, which is similar to previous one. So so uh, so I tried reducing the testing percentage, hidden layers, and also the number of neurons used here. So these are the results. um, this is the graph. The data frame length is that amount. The complete length of the sequence plus the numbers makes up the current number. There should be 1980 data points in total. The next step is to determine the data points index within the 2054 data points to make up the entire set. We must determine the index less the length of the testing data in order to divide the data set. So the data points had an index of 604 all the way to the end. To split the data, we will use iloc here. So the index is 1979. So the same model has been used, the compile model using Adam optimizer and MSE. 50 historical data points are used in the test data to make predictions. So the information to record 5 data and the most recent 5 records of the training must now be displayed. The data must now be normalized into range from 0 to 1. We can perform better. The min-max scalar class and the tool will be used. So this is a visualization for performance after training. The number of features must be specified in the project phase. The term feature refers to the dataset's number of attributes or variables and the closing features. Before using the straightforward RNN layer offered by Keras, we will employ the LSTM layer in the neural network. Okay, to feed data into another layer, we must configure the written sequence. The shape of the three-dimensional input must then be specified. So created time series generator for forecasting. The build, compile and fit LSTM model for forecasting has been done. So 40 steps has been checked. We will run 40 batches and then during the initial iterations, and the loss is 0.0011. Loss decreases in size. So this is the final graph for the actual and the predictions. So here the changes that are you done for redesigning this is the test percentage is the same, and the layers, 2 layers of LSTM layers are used. The neurons has been set to 50 and the dropout layer percentage is 20. Length of the time series input sequence is 2479 and batch sizing for training is set to 40. Batch size for testing is same as the previous design, it's 1. Number of epochs for training is 70, whereas in the previous design it's 100. So the major comparisons on this in both LSTM performances are in part 4 training loss started at 0.0521 and decreased to 0.0021 by epoch 10 eventually. Final loss stabilizes between 0.0008 to 0.0011. The prediction behavior, the network predicted trends closely matching the input sequence but with slight deviations during peak values. The forecasting, a decline trend in the forecasted data was observed, suggesting the model capturing long-term patterns but did not align fully with market trends. In part 5, the training loss started at 0.0032 and decreased to 0.0011 within 40 epochs, eventually stabilized around 0.0010. The final loss stabilized between 0.0010 and 0.0013, showing slightly higher loss compared to part 4. Prediction behavior, the redesigned network performed adequately but with a longer input sequence. The results slightly smoothened or out short-term trends, capturing long-term trends better. Forecasting, the forecasted values demonstrated better stability in long-term patterns, but the model failed to capture short-term fluctuations. So the observations and explanation in these two parts, changes and their effects. Reduced number of LSTM layers, decreasing from 3 to 2 layers slightly reduced the model's capacity, which may explain the higher final loss and reduced ability to capture complex short-term patterns. Increased input sequence length, extending the input sequence length from 60 to 2479 improved the model's ability to learn long-term dependencies but at the expense of short-term fluctuations. fewer epochs. Reducing the training epochs from 100 to 70 ensured quicker convergence but limited the model's fine tuning capability. A larger batch size, 40 instead of 32, improved computationally efficiency but might have reduced the granularity of weight updates. The final conclusion between these comparisons, there are some improvements achieved and there are no improvements. The improvements are found at the redesigned network showed part 5 showed improved performance in capturing long term dependencies due to the increased input sequence length. Forecasting was smoother and more stable, which may be beneficial for datasets requiring long term trend analysis. So, no improvement. The redesigned network struggled with short term fluctuations due to reduced capacity. The final loss of the redesigned network was slightly higher than the original, suggesting a trade off in predictive accuracy. So, the seventh part is about the project report, which has introduction and what I have done in all the parts and the conclusion. So, this project aims to explore the application of recurrent neural network and LSTM networks for time series data analysis and forecasting. By leveraging the strengths of these neural network architecture, the project seeks to predict stock price trends based on historical data. The stock price data set serves as a foundation for the models which are trained, tested, and optimized to provide accurate forecasts. This report documents the design, implementation, and evaluation of the neural network, highlighting their strengths, weakness, and potential areas for improvement. So, as already discussed, the final few points of this presentation is what I have done. In part 2, it's about simple RNN. A simple RNN was constructed to understand its effectiveness in capturing temporal dependencies. The model was trained on sine wave data to evaluate its ability to learn sequential patterns. So, the key steps discussed are building a two-layer simple RNN architecture with one RNN layer and one dense output layer, training the model, testing the model, and the result shows that simple RNN are capable of handling short-term dependencies but struggle with longer sequences due to vanishing gradient issues. Next is about LSTM neural network. LSTM neural networks were introduced to address the limitations of simple RNNs, particularly their ability to retain long-term dependencies in sequential data. The model's architecture was explained already, and the role of forgot input and output gates in managing information flow, advantages of LSTMs in capturing complex patterns in time series data. Coming to the fourth part, as discussed, LSTM with the time series data was an LSTM model was applied to the stock price data set to predict future trends. The model design has a 3-layer LSTM architecture, each followed by a dropout layer to prevent overfitting, a dense output layer to make predictions. The key parameters such as 10% of data reserved for testing, 50 neurons per LSTM, 20% dropout, an input sequence length of 60, a batch size of 32, and 100 epochs for training. The model demonstrated effective learning, and this has been redesigned by changing few points like reducing the number of LSTM layers from 3 to 2, increased the input sequence length to 2479, and batch size is increased from 32 to 40, and number of epochs were reduced from 100 to 70. The redesigned network showed some improvements. So this is my learning from this project, and this is the conclusion. I would like to conclude with as this project demonstrated the application of RNN and LSTM models for time series analysis and forecasting. The simple RNN model provides insights into the limitations of traditional recurrent architecture, while the LSTM network showcased its ability to effectively capture long-term dependencies. Thank you.